thank you all for coming to the next in our series. It's an exciting day. So, pleased to introduce Will Hamilton, who's a Mila in Mila and CFAR AI chair in St McGill University. He's known for graph databases, and he happened to be he only won the best paper, the best PhD award at some obscure junior university, Stanford, I think it was. Stanford Junior University. So it's pleasant to welcome him here.
Thank you very much. So today I'm going to be talking a little bit about some work I've done on graph neural networks, and in particular talking about a little of the theory of the representational power of graph neural nets and how that relates to some more traditional work on graph isomorphism and how we can use connections between these things to understand graph neural nets a little bit better. And I want to say before I begin that the work I'll talk about today is largely based on a paper here that's published at AAAI, and I mention that very importantly because the lead author on this, Christopher Morris, is the one who was responsible for running the experiments and doing really the bulk of the work. So it was also a collaboration with a number of other researchers, both at TU Dortmund and WPH Atkins. So all of them were really important, and I should say that this was really fun and interesting collaboration, as you'll see as the talk goes on, because we got to combine efforts from some people who are working on graph neural networks, as well as some people who are longtime experts on more traditional graph methods, things like graph kernels and graph isomorphism. So graph neural networks, they're really becoming the dominant paradigm or the dominant framework for what you could call graph representation learning. And for those of you who are familiar with graph neural nets, I will give kind of a brief high-level introduction to them in the coming slides. But they're a really fast-growing area. They've achieved state-of-the-art results in a number of different settings. So things like trying to classify the nodes in a network. So for example, suppose you're trying to classify the function of a protein based on its position within a protein-protein interaction network, or trying to classify maybe a user on Twitter as whether or not they're a bot or a human based on social network structure. Link prediction is another very big application domain of these techniques. So here we're trying to predict whether or not there's a relationship between two entities. So recommendations or recommender systems being a special case of this. So friendship recommendation, lots of applications in computational biology, for example, for computational drug repurposing. And then a really large application area that's been picking up a lot of steam recently. And for example, at NeurIPS, when we had the workshop on graph representation learning, was probably the most well represented is applications of these kinds of techniques for computational drug design and, say, trying to develop or generate new kinds of molecules. And so this is a really active and growing area. And so the theme for this talk is kind of taking it for granted that these approaches are empirically working well and they've had a large impact in recent years. We want to ask the question of what are the theoretical limits of these models, and in some sense, can we get an understanding of what graph neural nets can and cannot do from a theoretical perspective. And so graph neural nets kind of visually have this kind of structure that I'm showing here, and I'll unpack this both in terms of this figure as well as in terms of actual equations. So in a graph neural net, oftentimes what you can think of our goal is that we want to generate some representations or some embeddings for all the nodes in our graph, and we want these embeddings to encode information both about the structure of the graph as well as any feature information that we might have at all of our nodes. And we also might be interested in learning over the entire graph, and we can do that by, say, aggregating over these representations that we've learned for all of the nodes or vertices. So how this works is that if I want to generate a representation for some target node, say A, in this input graph, the way that this is done is that to generate a representation for node A, I'm going to aggregate information from A's local neighborhood in this graph, so from nodes B, C, and D. And then in turn, the information that B, C, and D are sending to A, so we often call this neural message passing. So the messages that A is receiving from its neighbors are in turn going to depend on messages that they're receiving from their neighbors, and so on. And so what I'm showing here is a two-layer or a two-iteration version of a graph neural net. And what this means is that at the end, after running this thing, the representations for all of my nodes are going to depend on information in their two hot neighborhoods, so their neighbors and their neighbors' neighbors. And one other important point is that we call this Instead you have neural message passing. At every step, nodes are aggregating information from their local neighborhood. But all of these messages are being passed forward in the computation graph. And so what this means is that it's a bit of a sticking point sometimes, because it's important to note that the node A here is occurring in the computation graph to generate the representation for node A. But the important thing is that at every step of the message passing, or every layer of my graph neural net, I'm generating new representations for all of my nodes. And at the initial layer, the way that I'm grounding this process is I have some kind of input features for all of my nodes. So it's perhaps easier to understand that component in terms of the actual equation. So here I'm going to introduce what I call a basic graph neural net. There are many varieties of graph neural nets. Almost everything I'll talk about today will apply to the vast majority of graph neural net models published in the last few years. But it's easiest to talk about things with respect to this basic graph neural net model, which was a variation of this first proposed by Scarcelli and Gore in 2005 or so. So the idea here is that we're going to initialize some representations, some hidden representations H. For all of our nodes, they're going to be equal to some input features that we have. We assume we have some input features X for all of our nodes. We initialize our 0-layer embeddings for every node as being these input features. And then to get the tth layer embedding, or the representation of a node at the tth step of what we call neural message passing, this is going to be a nonlinear function of information that we're aggregating from this node's local neighborhood, as well as some information from this node's representation at the previous layer. So what this means is that at layer T of this graph neural net, my node's representation depends on the neighbor's embeddings from the previous layer, as well as its embedding from the previous layer. Where here, we're doing all of this just by taking the sum of the neighbor information, applying some linear transformation, and then applying a nonlinearity, which is usually a rectified linear unit or a tan H. And now in this talk, I'm going to be focusing on graph classification tasks because it's easiest to characterize the power of graph neural nets in this context. And here, again, there are many things you can do to take a set of node embeddings and then pool those together to get a representation for a graph. And again, almost all of the theoretical results we'll have today generalize to most approaches. But for the sake of simplicity, we can assume that we're doing the most naive thing, which is that after we ran our graph neural net and got embeddings for all of our nodes, we then represent the entire graph by just summing the embeddings for all the nodes in that graph. And I should say it's actually important that you do a sum and not an average here, because if you do an average, you lose information about how many nodes are actually in the graph. And so it's actually important to do a sum, but other than that, you can use a wide variety of different approaches to learn these embeddings. And what we do then, once we have this embedding for the entire graph, we can use this for any kind of graph classification task. So some of the ones I'll talk about later on are things like trying to classify the property of a molecule, whether or not this molecule is soluble or toxic, and so on, based on its graph structure. So we're going to assume that we're training these things in some end-to-end differentiable fashion on some kind of classification loss. But the questions that we're going to be interested in within this context of classifying graphs using these neural networks is, for one, how powerful are graph neural nets, and in particular, are there limitations in terms of the kinds of graph structures that we can learn about using GNNs? And then, as an addendum to this, we're going to ask, is there any way that we can make graph neural nets provably more powerful? And so the way that we're going to investigate the power of graph neural nets is by looking at the problem of what's called graph isomorphism. So graph isomorphism is a kind of deceptively hard task, where the idea here is that we're given two graphs, and so I have these two graphs shown here, and here colors are just denoting the degree of the nodes. And the idea in graph isomorphism, I just want to ask the question is, are these two graphs actually identical? And unfortunately, now the slide decided to delete the top half, but didn't like the animation. So this task of just trying to figure out whether or not these two graphs are actually the same is seemingly easy. We basically just need to say, well, these two things match to one another, but it's not quite NP hard. Variations of this are NP hard. The classic graph isomorphism problem, people call it NP indeterminate. We believe it to be computationally hard. There are no polynomial time algorithms. But in general, the reason why this is hard is because what we're really trying to do here is trying to match two adjacency matrices. We're trying to say, if I have a matrix that represents which nodes are connected to which other nodes for graph 1, and I have the same matrix for graph 2, are these matrices actually the same? But the challenge is that I don't know how to order the rows and columns in these matrices. There's no natural ordering of nodes in a graph. We can order them in any way that we want. And so what this requires is we, in some sense, need to search over all possible permutations of node ordering. And this is why graph isomorphism is a hard problem. And here we're going to use it as this lens to investigate the power of graph neural nets, because in addition to being a computationally hard problem, it's also an interesting problem for trying to evaluate the power of a graph representation. So in particular, if we can say that with this way of representing a graph, we can solve isomorphism, or we can say that these two graphs are isomorphic if their feature representations generated by this algorithm are the same, then we know that this feature representation is maybe powerful enough to solve graph isomorphism for some reasonably large subset of graphs. So oftentimes, if we're asking about ways to represent graphs as feature vectors, it's an important question to ask is, does that feature representation generate the same representation for two graphs that are isomorphic, but generate different representations for graphs that aren't isomorphic? And of course, there's no perfect feature vector, but we can evaluate the cases where these things fail and where they don't fail to get a sense of the power of a particular representation. And now, we're going to build off historical work on graph isomorphism, and in particular, we're going to talk about an approach to isomorphism testing, or generating discrete feature vectors of graphs. And I'm going to mention this, for one, because it's one of the most popular approaches to graph isomorphism, but also because of the fact that graph neural nets are going to have a very close relationship to this algorithm, which is called the Weisfeiler-Leman isomorphism test. And so this is one of the most studied versions of trying to do graph isomorphism. And what this algorithm is called, the WL test. It's also been called naive vertex coloring. And it's actually a relatively simple idea that is able to solve graph isomorphism in a wide variety of settings. So the way this works is that we're going to color all the vertices in our graph, or all the nodes in our graph, based first just on their degree. So now we've colored all the blue vertices have 3 edges, the red vertices have 2 edges, the green has 4. And the next thing that we're going to do is we're going to iterate this coloring, where now we're going to color our nodes based on the set of colors in their local neighborhood. So now this red node in the middle, it has a blue neighbor and a green neighbor, so it gets a label that says, okay, it has blue-green. In particular, this label's a multi-set. So it's a set, but we're allowed to have replicated entries. And then we get this for the green node, we do this for all of our nodes, and now we have a representation, or a little label each of our nodes that tells us what are the degrees in this one-hop neighborhood. But we can do this again, and we can say, get labels of now what are the labels of the previous iteration and aggregate on those, and now we're saying for this red node, its neighbor had this blue, red, red, red label, and its other neighbor had blue, blue, red. So now we're going to have another set of labels, which is aggregated over the labels we got from the last iteration, and so on. And we can iterate this idea, and if we summarize this into an algorithm, it's relatively straightforward. So what we do is that we initialize every node with a color, or an integer, corresponding to its degree. And then we just iterate this algorithm where for t steps, what we do is that for each node, we're going to generate a new label for that node, which is just a hash of the multi-set of labels within its local neighborhood. So this is, we call this coloring, but in general, if you actually implement this, you're just going to use integers and hashing. And the basic idea is that we can run this algorithm for t iterations, and then after we ran this algorithm for t iterations, we can generate a multi-set representing a graph, which is what is all of the labels, all of the colors or integers that we obtained for this particular graph. And we can compare two graphs by saying, are the multi-sets that we got at the end the same? If they are the same, we can say these graphs are maybe isomorphic. You can also use this as what we call a graph kernel. So you can represent graphs in a feature vector by taking these sets and turning them into histograms, essentially. So there's various different ways of trying to convert these multi-sets into, say, histograms or some other feature representation. But this is a very, very powerful, one of the best non-deep learning approaches for machine learning on graphs, is you run this algorithm, you generate these multisets, and you turn these multisets into feature vectors in some way, and you use those as a feature representation for your graph. And now, one thing that's important to note is that there's really this close correspondence between the graph neural network algorithm and this WL coloring algorithm. In particular, in this WL coloring algorithm, what we do is that we initialize every node with a discrete label. In the graph neural network approach, we initialize every node with some feature vector. And then in the WL algorithm, we iterate this process where for every node, we give it a new label, which is a discrete hash of the labels in its neighborhood. In a graph neural net, we do the same thing, just a differentiable version of that. In a graph neural net, for every node, we generate a new embedding, which is a neural network that's a neural network applied to the set of embeddings in its neighborhood. And so really, graph neural nets are essentially a differentiable, a neural network version of this WL isomorphism test. And this is no accident. Interestingly, graph neural nets were originally concurrently developed as a differentiable version of belief propagation and probabilistic graphical models. They were also developed by people in my lab as a differentiable version of this WL algorithm, but they're also developed independently as an approximation to spectral graph convolutions, and as a very neat kind of confluence of mathematical ideas. The graph neural algorithm that you get in the end is the same no matter where you started from these different intuitions. But I just want to say it's no accident we developed some of the early graph neural nets based on this correspondence. But the thing that's important for this talk and for these questions of characterizing the power of graph neural nets is that we can actually use this correspondence between graph neural nets and this classic isomorphism test as a way to characterize the power of GNNs. So in particular, if we consider this basic graph neural net architecture that I described at the beginning, and we make one relatively mild assumption, which is the assumption that our input features are node degree. In fact, you don't really need to assume this. You can assume you have constant input features or you have random input features, as long as they're not the same for all your nodes. And what you can say informally, the theorem statement, is that if the WL test can't distinguish, if a WL test can distinguish between two graphs, then our graph neural net can also do that. And if a WL test succeeds at detecting graph isomorphism, then our graph neural net can also do that. And really what this means is that there exists a parameter setting of our basic graph neural net where it essentially does the same thing as the WL kernel. And this is not particularly surprising. In some sense, it's not that hard to imagine that there's a way to set up the parameters in these matrices and a way to make this relatively high dimensional using, in fact, you have to use a ReLU activation function, and I believe our theory collaborators have generalized it to also tanh and sigmoid. But there's a way to set all the parameters for this thing where it basically behaves just like that discrete coloring algorithm. It requires maybe a lot of parameters, but it's possible to do. So this is a good result. This tells us that, well, we know that we base graph neural nets off this WL coloring algorithm, and as we would hope and expect, graph neural nets are capable of doing just as well as this WL test. But the interesting other direction, so the other direction of this if and only if statement, is that graph neural nets are no more powerful than the WL algorithm. So it's not that adding deep learning has made this somehow magically better. In fact, you can prove not just a basic graph neural net, but any graph neural net where we have some differentiable permutation invariant function that aggregates information from our local neighborhood, and any differentiable function which uses the information aggregated from our neighborhood as well as our node's previous representation, generate a new representation. So this is pretty much every graph neural net, except for some graph neural net that has been specifically designed to avoid this issue, in particular with the permutation invariance assumption there. Any graph neural net of this form is no more powerful than the WL isomorphism test. So in particular, if a WL isomorphism test fails at telling whether or not two graphs are isomorphic, then this graph neural net's also going to fail. And this is somewhat important because this tells us that in a really kind of strong, discrete sense, there's nothing magic that we're gaining from using these graph neural nets. There may be benefits from having the end-to-end differentiable ability, But if we're generating a representation for our graph based on traditional WL kernels or based on a graph neural net, and we're talking about kind of worst case representational ability, which is kind of what this graph isomorphism test is getting at, there's no benefit to using graph neural nets. Although I should say there are benefits in practice.
So this is permutation of the neighbours. There's also permutations of in the embeddings. So how do you handle because presumably there's different permutations of the embeddings.
Oh, within the embedding dimensions.
Yes.
So
you have to test that too, don't you?
No, so we actually didn't look into that. We haven't looked into that in detail. So here we are assuming that in some sense the dimensions of your embeddings are kind of fixed. And in some sense those need to stay fixed, at least is my intuition for it, in order, for example, for us to even have the result of this thing being as powerful as the WL. But it is important that it's interesting, and maybe to jump ahead a little bit, that in some sense when we're aggregating information from our local neighborhood, so we have a node that says, okay, I want to take information from all of my neighbors, implicitly that is a set function, or it's a multi-set of information in my neighborhood, and there's no natural ordering over those nodes. And so it makes sense to use some kind of permutation invariant function. But in fact, you can build graph neural nets that I won't talk about in this talk, but that would actually follow up on this work by Bruno Ribeiro and others at Purdue. You can build graph neural nets where you use permutation sensitive functions, and then in some sense you have to average over all permutations, and that's provably more powerful than the WL test. So that's work that actually came out in ICML 2019, so just after this. And so why is this limitation? So you might ask, okay, well, in this worst case sense, we're no more powerful than the WL test, but does it actually matter? So is this just some kind of weird adversarial worst case examples that we're talking about? And so I want to point out that the WL test is very powerful. It's one of the best, or certainly classes of graph isomorphism algorithms out there. And it's known to succeed on almost all graphs. So the set of graphs that it doesn't work on is kind of a vanishing subset compared to the rest of graphs. But it fails in some pretty bad cases. So I think one of the most interesting cases where the WL test and graph neural nets fail is that if I'm trying to distinguish between these two graphs, so one is a cycle of 6 nodes and one is 2 triangles, no graph neural net can tell these two things apart. And the way to look at it is that when you're looking at it from the perspective of, say, this node, it knows that it has 2 neighbors that are degree 2, but it doesn't know that these 2 neighbors are connected to one another. It just knows it has 2 neighbors of degree 2, and that argument extends to all the nodes on this cycle. And this is actually really important because what it's failing to do here is it's failing to detect what we call triadic closure. So a really important property of real-world networks is that people who are friends of friends tend to be friends with one another. Proteins that interact with another protein, and those 2 proteins tend to interact. You tend to have these closed triangles in real-world networks. That is far more prevalent than you'd expect, say, from a random graph. And an issue is that graph neural nets at this kind of local node level have a really hard time telling whether or not their neighbors are neighbors of each other. And so this is seemingly maybe not that big of a deal. Again, in a mathematical sense, these kind of adversarial graphs that GNNs fail on are a vanishing subset of all graphs, but they're a pretty important vanishing subset, especially because of the relationship to triangles. And now one final point I want to make before we get into kind of trying to improve on top of graph neural nets and make them more powerful, at least our first approach at this, is that despite the fact there are these negative results, and despite the fact that I said that graph neural nets are no more powerful than this WL algorithm, there are benefits to representation learning. So in this worst case sense, graph neural nets are no more powerful, but learning continuous representations might be a much better thing to do in lots of cases. So in particular, if you're trying to run the basic WL kernel, what you do is you do this big discrete coloring algorithm on your graph, and you end up with these huge multi-sets that you have to turn into feature vectors in some way, or histograms. And these things can be really big vectors. There's no easy implicit kernel to represent them. You have to use the explicit feature vectors. And it can be kind of messy. There's all these choices you need to make in terms of how you encode these things. Whereas the elegance of graph neural nets is that we're just learning some low-dimensional continuous representation that can approximate the same information. So there's certainly an engineering elegance to them, and graph neural nets may also, as an open question, be able to represent similarity in a fuzzy sense better. So we're talking about strict, are these graphs the same or not? But maybe in terms of kind of fuzzier versions of similarity between graphs, we get benefits from the representation learning. I would say the jury's still out on that, and some of the results I'll talk about today are actually somewhat negative. And finally, I guess it's not listed here, but one benefit of graph neural nets, and in my view, probably the biggest argument for using them compared to these traditional graph kernel algorithms, is that they're really easy to use in conjunction with other learning approaches. So in particular, if you suppose that you have, say, image features on your vertices, you can have a convolutional neural network that's generating representations at your nodes, and then you can have a graph neural net on top of that. There's no easy way to do the WL algorithm on top of a CNN, whereas the benefit of graph neural nets is they play very nice within more general deep learning ecosystems, which certainly today has a big impact. I should say, if there's any questions throughout, do feel free to interrupt. Okay. So now we've characterized the fact that graph neural nets are powerful, but maybe not that powerful. They have their limitations. So now there's the question of how can we generalize graph neural nets to maybe make them more powerful. And here, in this initial attempt at this, and I'll say that in the 8 months since this has happened, there's been some really nice work by Bruno Ribeiro at Purdue, as well as Yaron Lippman, on other ways that we can generalize graph neural nets that are perhaps more elegant than this. But in this first approach, we took what is maybe the simplest approach given where we started, which is that we tried to think about, okay, how have graph theorists tried to make the WL test more powerful? And maybe if we see what they've been doing with the WL test, and in traditional graph isomorphism, we can do similar things to make the graph neural nets better. And in particular, in graph isomorphism, there's not just this WL algorithm as I've described it. There is actually a whole class of these algorithms that get more and more and more and more powerful. And they're generalizing from the WL to what's called the k-WL test. And the idea here is that instead of labeling nodes, so instead of doing our kind of message passing at the level of nodes, we do this at the level of subgraphs. So for example, for the 3WL test, there's 3 possible graph structures of size 3. So there's 3 possible size 3 subgraphs. We can have a connected triangle. We can have just a chain. We can have 1 isolated node and 2 connected nodes, or 3 isolated nodes. And what we're going to do is we're going to look in our graph and find all the instantiations of these different subgraphs. So here there's all these different connected ones. We see many examples of chains. There's many examples of places where we have 2 connected nodes and 1 disconnected node. And there's many places where you can find 3 disconnected nodes in this graph. And what we're going to do is we're actually going to label every possible subset of 3 nodes in our graph according to which of these 4 structures it is. And then we're going to do a version of this coloring algorithm where now we're doing it at the level of subgraph. So in particular, what we've done is we've labeled every induced subgraph by its isomorphism class, is actually what we're doing here. Then we're going to run T iterations where at every step we're going to say, okay, at iteration 1, the label for my subgraph is going to depend on the labels of the subgraphs that are neighboring of this subgraph, and so on. So the same idea we did for nodes, it's a bit harder to visualize now, but doing this for subgraphs. One challenge here is that the notion of a neighbor is not as easy to define. So a neighbor of a node is a node it's connected to. A neighbor of a subgraph, in a formal sense, is any subgraph that differs by exactly 1 node. So in particular, if we're looking at this subgraph here, this is a neighbor, and so on. And what you can do is with this generalized notion of neighbors, with this generalized notion of instead of at every step you have nodes aggregating labels, now we have subgraphs aggregating labels, you can run this whole thing, what we call the k-WL test. And what you can prove is that this k-WL algorithm is provably more powerful than the 1WL. For any k greater than 2, I should say, k equals 1 or 2 are equivalent. And for any k greater than 2, you can always find a pair of graphs where the k-WL fails, but the k plus 1 WL succeeds. So this is really nice because you have this spectrum of complexity where you start off with the simplest one, and then there's this hierarchy of how powerful these algorithms are. I should say that this doesn't mean that we've solved isomorphism, because solving the k-WL requires solving graph isomorphism for graphs of size k. Because we need to, when we're labeling the subgraphs in the graph, we have to label all different types of subgraph structures, which is as hard as solving isomorphism for graphs of that size. So This means that, of course, we can do things that are more complicated, but you're not going to run the 50 WL because that's going to be as hard as just trying to solve graph isomorphism in the first place.
But surely this is n to the k, the order of magnitude of this is...
Yes,
And
yes.
it ends...
It's extremely, yeah, it is
So
n
you
to the
can't
k,
have a
yes.
big graph.
Yes, it is. It's at least n to the k, because it's n choose k.
Yeah.
Yeah. Yeah, so it is not, and this is, in practice, nobody goes higher than the 3 WL. So the 3 WL is commonly used, but in practice, nobody goes higher than that. And so I say, can we generalize one graph neural nets to k graph neural nets, but really, this is more saying, can we generalize to, say, like a 2 or a 3 WL? We're not going to go higher than that.
Sorry, just
Yeah.
try to follow. So, what do you mean by one algorithm is more powerful than another?
Oh yeah, so what we mean by more powerful is that so if you have the KWL, you can always find a pair of graphs that are not the same where it thinks they're the same.
Okay.
And then if you do a K plus 1 WL, then you'll be able to find, when you make K high enough, you'll be able to detect that those graphs are actually different. So by fail, we mean, usually when we're talking about failure here, it's when we're mapping two graphs to the same representation when they're not actually the same. And so you always find a pair of graphs where you'll fail, and then you can keep going up. But again, it's kind of a vacuous thing if you make K too big, because at some sense you end up having to solve the original problem again.
So that means if suppose we are looking at in chemistry, if you are looking at how the chemicals are bonded together, it could be a double bond or a single bond. Even that needs to be taken into consideration, right?
Oh, this is a great question. So I should have mentioned this at the beginning. So we're talking only about simple graphs here. So with only one type of edge and with no self loops, which isn't really important, but it's true that it is, when you start adding different types of relations, there's generalizations of these algorithms to these cases. And in some sense, there isn't anything fundamentally different, but it does get more complicated, and generalizations to the KWL when you have more different types of relations are even, the combinatorial explosion just goes up and up and up. But it's true that even for the regular WL test, you can generalize it to having multiple types of relations, and it's not that difficult, but it makes things, at least bookkeeping, a lot more challenging. So for this, I'm focusing on simple graphs, and we don't have a good way of how to generalize to k-GNNs on multi-relational graphs, but we can handle multi-relational graphs with regular GNNs. It gets hard when we're doing this generalization.
So everything so far, like you're talking about expressibility versus learnability.
This is another great question. So everything so far is only expressibility. And I think that the questions about learnability, and this was something maybe I was going to bring up at the end, but I'll talk about now. So there has been a lot of work on the expressive power of graph neural nets in relation. So here with the WL test, you can connect this to logic as well, because of the fact that certain subsets of first-order logic are actually closely related to the WL test. So there's actually an iClear submission right now on analogous proofs of expressiveness with respect to logic, as well as dynamic programming by Stephanie's group at MIT. But these are all that it can express these things. And in practice, does it learn to do the right things, especially when it comes to, say, logic? In my view, is that not always. And in particular, one of the challenges here is that there is, I think, kind of catastrophic overfitting that can happen, where even though we know that the graph neural net is capable of representing these logical formulas, for example, if you train it on a bunch of supervised examples where it needs to solve those logical formulas, it instead just overfits and kind of hashes in ungeneralizable ways. So questions about learnability, and in particular, what are the right ways to regularize and train these things so that they learn to be as expressive as they can be, is an open problem. But I will say that when it comes to the connection to the WL test, there it's basically, the question is, can we hash every unique subgraph to a different value? And we know that that's actually pretty learnable. We have done some empirical studies on that, not in this work, but later on. So there we have some empirical sense of learnability. but learnability for some of the more interesting questions, like representing logic and representing dynamic programming, is a bit more of an open question. Okay, so when we're talking about this generalization going from graph neural nets now to k-graph neural nets, the algorithm here, which I won't spend too much time on because I would like to talk about some of the empirical results because they're kind of fun in terms of comparisons to baselines. So what we're going to do here is we're now going to say that we have our initial representations are on subgraphs, and then what we're going to do is we're going to do this neural graph message passing idea now over subgraphs. We have a couple challenges here. The first challenge is how do we define the initial features over subgraphs? We're given features over nodes. How do we get features over subgraphs? And the second problem is that if we're going to do this message passing over these subgraph neighbors, that's going to be just extremely computationally expensive. As we discussed, the number of neighbors is basically n choose k for each of these subgraphs, and so that's going to be huge just in terms of computational expense. So the way that we deal with two of these, or both of these problems, is first off, we use what we call a hierarchical k-GNN. So what we do is that we run a one graph neural network to get representations of nodes, and then we aggregate those representations together to get representations of subgraphs. So we just take their average or their sum. So that's actually kind of nice. That's the one place where we can, again, leverage this kind of differentiable nature of these things, is we can actually stack these hierarchical k-GNNs and train the whole thing end to end. The other thing that we do is that rather than just using the formal graph theory definition of neighbors between subgraphs, which is combinatorially explosive, we use a more practical technique that people have used for developing graph kernels, which is we say that two subgraphs are neighbors of each other if they share at least one node and there's an edge connecting nodes, at least two other nodes in that graph, in the subgraph. So it means that sometimes called like the local variation of the KWL test, which has been very successful for generating, say, graph kernels, for example, in Christopher Morris's previous work. So this is how we define this generalization of graph neural nets, which was somewhat of an empirical exercise to see if we could do better, but also kind of a theoretical exercise in trying to understand whether or not these ideas of making them more expressive, kind of in the best case, actually leads to models that learn better in practice. And so when we look at our experiments, what we did is we looked at some standard graph classification benchmarks. We should say that some of these benchmarks are not the most exciting benchmarks because they're relatively small graphs, but they're very well understood from the perspective of evaluating classic graph kernels. And we were interested in three questions. So one, we wanted to know, do these k-graph neural nets provide any benefit over our graph neural nets in terms of actual performance? A perhaps more interesting question is, do k-GNNs or GNNs in general actually provide any benefit over these kernels? So as I said in the beginning, we know that graph neural nets are provably no more powerful than these kernels in a kind of expressive worst case sense. So do they actually provide any benefit in practice? And in particular, we were very lucky in this work to have some of the best researchers working on graph kernels collaborating with us, which meant that people were actually spending a lot of time making sure that the graph kernel baselines were implemented well, and that we weren't in some sense cheating when we were comparing against these previous approaches. And then the last point, which is not something that I talked about in detail, but I think is a really interesting point, is the third question is, how much does training a graph neural net actually matter? So what's interesting is that another consequence of the theory in this work is that a randomly initialized graph neural net is in expectation as powerful as the WL test. Just using random parameters, it's going to, if you just initialize everything randomly, which is say Gaussians or Xavier Glowroth style initialization, in expectation it does something that's basically like hashing. And so there's a question about whether or not graph neural nets even need to be trained, or can we do as well with the untrained graph neural nets. So first off, I'm going to talk about mainly the first question, which is there any benefit of this k-GNN compared to these other graph neural nets? And here we're looking at what's called the QM9 data set, where the goal here is we're given a graph structured representation of a molecule, and we're trying to predict some molecular properties. So for example, the solubility of the molecule and a number of other things. And without dwelling on these results too much, so we have a set of different target properties. and comparing here to a number of different baselines from the graph neural net literature, and then our own implementations of a 1-GNN, a 1-2-GNN, a 1-3, and a 1-2-3, so different kind of hierarchical variations. And then on the right is the gain that we achieve from the hierarchical GNN compared to the 1-GNN implementation. And what we did find was that in this relatively, as fair as we could make it set up, there was often gains actually to using this hierarchical GNN. We did match things in terms of number of parameters, but there is a lot more runtime for the hierarchical GNNs. So we decided to kind of match for fairness on number of parameters, but you still do pay a penalty, pretty big penalty in terms of runtime. So what I think is somewhat more interesting is our results. So that was on these molecular graph benchmarks, which are very popular in the graph neural net community, and where it's well known that the graph kernels are not necessarily the strongest performing methods for a variety of reasons of them not dealing with node features very well. But now what we decided to look at is a series of more standard graph kernel benchmarks. So these are data sets that have been collected by actually the collaborators of TU Dortmund. And these are a bunch of different types of graphs. So these are protein graphs on the far left, different graph representations of IMDb database. MuTag is enzyme. So a number of just graph representations of various types of objects. And we always have some classification task on them. And all of the results here being in AUC. And what we're comparing is, first off, the best graph kernel methods that we have. So these include variations of the WL test graph kernel, as well as what's called the graphlet and shortest path kernel. So the graphlet kernel is relatively intuitive. It's basically just counting how many different types of subgraph structures of size, say up to 3 you have. So how many closed triangles versus chains and so on you have in your graph. And then the different variations of the WL test, or WL kernel, as well as what's called the WL optimal assignment, which is a variation of the WL kernel. And then we were comparing against some previous state-of-the-art graph neural network or graph convolutional network or variations of algorithms in this space. And then our own implementations of graph neural nets, including graph neural nets that we did not train, where all we did was we kept the graph neural net parameters fixed, ran a 2 or 3 layer graph neural net, and then just trained the logistic regression at the very end, the final softmax. So I think the first key thing that I want to point out is that on the whole, if we're looking at what's bold in this table, it's mainly the simple kernel methods. So a well-tuned version of these graphs, and I should say all of these are also, I should have the standard deviations, but these are all cross-validation results where it's this kind of nested cross-validation to do hyperparameter optimization of the graph kernels are using SVMs on top of them. And so on the whole, when you do a good job, and in particular when you use nice, well-tuned SVMs as opposed to just logistic regression, the graph kernels drastically outperform most of the state-of-the-art graph neural net techniques, except for Pachysan in this one data set. So on the whole, the top performers were not graph neural nets. They were actually just traditional graph kernels. And what's interesting, even more interesting in some ways, if you look at the bottom, is that in many cases, an untuned graph neural net was actually outperforming previous graph neural net algorithms. An untuned graph neural net, so for example, an untuned 1-GNN, is actually pretty competitive and even outperforms our own tuned version in some cases. So this was a result that's since been replicated many times and actually a really strong baseline in a lot of graph tasks when you're trying to encode nodes is just using an untrained GNN. And I want to say that these are somewhat depressing results because our one key result is that, well, we can use simple kernels and outperform the state-of-the-art graph neural nets. The other thing is that we don't even need to train our graph neural net. But I want to point out that these are really small, simple data sets. These are all data sets where there's really no interesting node features. They're all data sets that they're small graphs with maybe only hundreds of nodes, and they're really not the place where we'd expect a really heavy hammer like graph neural nets to actually provide a benefit. And I know that in practice, graph neural nets do provide a benefit in many instances, and especially in instances where you have, again, really complicated continuous node features, and then you can't even use these graph kernels. And also when you have really interesting continuous node features, the gain you get from tuning gets higher and higher. But this is just to say that just because they're using some interesting kind of neural network or deep learning formalism doesn't mean that they're necessarily going to win in all cases, and in particular they don't win when we're looking at these very simple baselines. But this shouldn't be surprising because the theory tells us that these graph neural nets, basically that the trained graph neural nets, the untrained graph neural nets, and the graph kernels should be, in expectation, all equally powerful on these simple benchmarks. So just to conclude, so I thought the main, insight of this work is just trying to understand a little bit about the expressive power of graph neural nets in terms of what they can do and what their limitations are, to maybe give us a better sense of when they're going to work and when they're going to fail, and also some insights about challenges with them. So for example, this issue of detecting closed triangles, which is actually a really big practical issue for graph neural nets and social and biological networks. And I want to also mention work by Hege Maran and Weisfeiler-Leman on what are called G-invariant networks, as well as work by Ryan Murphy and Bruno Barbero, which give other variations of graph neural network-like models that are provably more powerful than graph neural nets and provably more powerful than the graph neural nets that we describe in this work. So there's been really interesting follow-up work in this space, some of which are actually doing a lot better on empirical benchmarks. And then lastly, I said it before, but again, which is that I don't want the takeaway to be we shouldn't use these things because they're outperformed by graph kernels. I think the important thing is that we want to keep in mind what their theoretical limitations are, and also when are the cases when they're going to be useful for us. And they're definitely very useful in all kinds of settings with continuous features, useful as an easy thing to plug and play within big deep learning frameworks, and so on. So they have lots of strengths, but it's probably worthwhile to focus on the strengths of these things, and I think in terms of benchmarks and where you're using these models, maybe trying to think in terms of larger data sets, more interesting, more rich data sets, than focusing on, for example, these traditional graph kernel benchmarks. And then lastly, as mentioned in the question, a really big and important direction for future work is extending these expressibility results with a lot more actual on the learnability of all these different types of graph neural nets. So with that, I'll take any questions.
Thank you. Okay, 10 minutes or so, questions?
In the beginning, you had a theorem for k equal to 1. Does it extend to...
Yes. So the question, so does the k equals to 1 extend to higher k's? It does, but not with the approximation that we introduced of only using what we call local subgraph neighborhoods. So if you run the full k-GNN, it is as powerful as the KWL, but it's empirically or computationally just so expensive to run that thing.
In the hierarchical version, did you try learning each of the layers separately with its own objective and then combining them, or did you just try learning all together with one objective?
Not that, so no results that were communicated to me by Christopher were on that setting of training them independently, but it was Christopher who ran the results, and knowing him, I actually would guess that he did try that, but I'm not certain what the results were. On the whole, I will say that given the fact that even not training at all, it wasn't changing it very much, and given the size of these data sets, again, I should have had standard deviations there. There's quite a bit of noise, so my guess would be that the difference you would get from that on these data sets would be within the noise of the cross-validation, or the variance of the cross-validation.
The graph isomorphism problem, can it be solved by feeding in some information that we already know based upon the field? Say, suppose in genetics we are expecting some kind of thing.
Yes, this is a really good question, which is that, and a really good point, I think, talking about what are the benefits of graph neural nets, right? Which is that here we're talking about this worst case expressiveness where you have no external information, where your node features are just what's the degree of this node. In practice, we often have interesting features, and when people actually try to do graph alignment in practice, for example, in biology, they leverage these interesting features. And so I think that it gets more difficult because your notion of what does it mean for two graphs to be isomorphic when they have continuous features, then in expectation no graphs are isomorphic to each other. But I think in practice, in terms of practical measures of learning on graphs, leveraging these interesting node features actually helps a lot in terms of doing good things in practice and is a big strength of graph neural nets because this WL kernel, WL algorithm can't deal with continuous features.
What I always found strange about graph neural networks is you always look a fixed number of steps ahead. Why don't you actually compute the markup chain? So doing that, why isn't that the obvious solution to this?
Yeah, I think so. We're working on that right now. I guess is maybe the answer.
Okay.
It's a little bit so. That is something that we're looking into. So in particular, thinking about kind of what are the steady states of diffusion processes on the graphs, and what does that imply? It's I think mathematically more, and if you want to have that be within kind of an end-to-end differentiable framework in the neural network style, it's mathematically a bit involved, and it becomes interesting because one of the big issues with graph neural nets, with the basic graph neural net that I talked about, and I mentioned this over lunch actually, is this issue of what we call over-smoothing, which is basically that if you run this graph neural net, you end up getting that all of, for too many layers, it ends up being that all of your nodes embeddings all kind of look the same. Right? Everything's basically, it's as if you've run random walks on your graph and kept them going forever, and you end up being that it's kind of over diffused. And so that's actually a big issue and challenge in graph neural nets is making them behave so they're not just like a really low pass filter on your graph. And so there's a big interest in this idea of kind of thinking about kind of these continuous time unrolled versions of them. But then we're thinking about that in conjunction with the fact that a biggest empirical challenge on making graph neural nets perform well is having them not be over diffused in this kind of signal processing sense. So there's an theoretically interesting, but then there's a challenge about it's going too far in that direction is maybe counter to the main goal. So should we wrap up and let the next person start?
All right.
Awesome.
Okay, thanks, Steve.